Right.
We don't really
Alright, so...
And then I looked at yours and it was different. Oh, she's probably right.
You trusted me. What do I know?
You know what? I trusted you now.
Okay.
I'm not doing too bad.
Okay. What? I didn't say a word.
Hey, what are you saying? What are the noises you're making? What are they?
I don't know if you're one to say that.
Yeah, I know. I don't think you're the I always describe that my noise.
I think that's the chimp calling the chimp the chimp.
Oh.
So,
Isn't that saying like the
okay,
pot
I'm
calls
Caesar, so.
the kettle calls the pot black?
alright, so let's talk about problem number 9. Okay? Okay, we will talk about that.
Second half.
Problem number 9.
I have a problem with problem number 9. Same.
Honestly, you should just take the last 2 to 3 problems off of every assignment.
Then we wouldn't have any questions.
Life would be so easy.
Okay.
Just put the hard one at number 1.
It's always number 9 we have questions on.
So, here's this ball, right?
Correct.
Up on top of a building. So what type of energy does it have just by virtue of the fact that it's above the ground?
Potential.
So we've got some which is MGH, right?
8 or 9?
No, 9. Well, that's a cliff, not a building, guys.
Look, I drew it.
You get the point of it. Go ahead.
Thanks, appreciate that. Now, if I just drop it, when it lands, what's it going to have? Kinetic. Okay? Because if you set up a chart and go, okay, well, let's look at this. So there's no springs or anything else, so I'm just going to have in kinetic, right? And then the sum. So if all I do is just drop it, up here I'm going to have X amount of potential energy. I don't know what it is, I don't care, it's just going to be a certain amount of potential energy. Am I going to have any kinetic energy?
Zero.
No. So the sum of that is going to be whatever my potential energy is. True?
Yes.
Good with this. Now, if I just drop it, when it lands, how much potential energy does it have?
0.
0. So it's all going to be, it's like tic-tac-toe, it's all going to be kinetic, right? Which is going to give me the same value of x. True?
Right.
Mm-hmm.
Okay.
You're speaking words of truth.
Thanks. Okay. But now, what if, let's just play the what if. What if I throw the ball straight up at some velocity? Okay? Is that going to impact the potential energy that I have due to gravity?
Yep.
No.
No.
Why?
Because it's still MGH.
God. But if it goes up higher,
Your height. Wait, what?
if you hold it
Okay,
here,
the initial potential energy.
oh,
And then you.
Okay? Now, so if I throw it up in the air, then this kinetic energy isn't 0 any longer. It's going to be a value. I don't know what it is. I'll just let that one be y. Okay? I don't know what it is. I don't care. So my total now becomes what?
X plus Y.
X plus y. So now I'm going to have potential kinetic and then the sum. Now, if I throw it up in the air, when it lands, do I still have no potential energy when it lands?
Yes.
Yeah.
Yes. But now when it lands, how much kinetic energy do I have?
X plus Y.
X plus y. So my sum is still X plus y. So if I throw it up in the air, throw it straight up, then it's going to land with more kinetic energy than if I just drop it. Because I just don't have potential energy. Now I'm adding to it with kinetic energy. Okay? What if I take this, and instead of throwing it up, I throw it straight down? Will that change my value of y?
Yeah.
How?
say it again.
Yeah.
Yes. That's always the answer.
Say it again.
Say it again.
Okay. So here's the golf ball, right? situation number 2, I'm on top of the hill, and I throw it, and I let it go like this.
No.
That will have a certain amount of kinetic energy, right?
Sure.
If I take this and I throw it down with the exact same velocity that I threw it up, will that change the kinetic energy of the ball?
The velocity doesn't.
No.
Velocity doesn't.
No, why?
Doesn't
How do you calculate kinetic energy? 1/2 mv squared. It's a scalar quantity, right? So whether I throw this ball up in the air or if I throw it straight down, guess what? It's still going to have the same amount of kinetic energy.
Why though? Because you're going to have more velocity if you throw it down.
No, he said the velocity.
The same.
Yeah.
The same velocity as if you threw it up?
Yeah.
Okay.
Now,
How do we get those?
what if I throw it out at a 45-degree angle? Is that going to change the amount of kinetic energy that it has?
No.
So does it make any difference which direction I throw it?
No.
No. So no matter which direction I throw it, this sum is still the same, right? Now, you're going, wow, I don't have the mass. Well, let's look at what we got. So we're going to look at UG plus my initial kinetic energy is going to equal my final kinetic energy, right? This is what we just said. It's going to have some potential energy because of its height. It's going to have kinetic energy because I'm throwing it. And this doesn't make any difference. As long as it's the same velocity, which direction I throw it, horizontal, down, up, doesn't make any difference. Then my final kinetic energy. What do I need to calculate UG? MGH. What about this kinetic energy? 1/2 m. Call that V naught squared because that's my initial. And then this is going to be 1/2 m V squared. So what can I get rid of? Masses all cancel out. If I multiply by 2, I get 2GH plus look familiar? It's just that equation. That's all you have to do is just use that equation.
Man, you just speak some words. Just
So,
Now, there's the long way that you can work this problem. Here's the long way to work this problem.
I like your tie.
This thing is launched at a 45-degree angle. So here's what you could do. You could come out here and you could find the Vx and Vy components of that velocity. Then you can use that Vy to get the maximum height. Okay? Then you can use that to figure out your impact velocity here. Okay? In the y direction. It's also going to have the Vx. Then you find your resultant velocity, plug that into 1/2 mv squared.
You said this was one of the simplest.
It is, because all you have to do is use v squared equals v naught squared plus 2ax. You can make it horribly complicated and break this up into x and y components and find the maximum height and find your resultant velocity and all this other stuff.
Why would you?
That's the point.
All right. Just
So number 9 should get you an answer around 200.
What?
Why are we so bad at this?
Because you started talking about all this different energy stuff, and I was like, wow, I did this wrong because I used that equation. And then I crossed it all out, and now to...
Do you really mean 200 or do you mean like 73? I got 73.
Oh, wait,
Okay,
square
I so
185.
don't. Kendra, if the answer was 73, I wouldn't say around 200.
I forgot to square one, it's
You
fine.
don't have to.
Got
We
it.
figured it
That's what
out.
I'm saying. You don't have to.
We work number 8.
So you just use 265.
Will you do
meters?
AE?
Yes.
Can you do all of 8?
Can we do all of, yeah.
Okay, let me show you some footage so you can get an idea of what's going to happen on number 8.
I need a lot
Footage?
of help on
Yeah.
We'll talk about it.
Okay. It's like so confused. I was sitting, I was like,
Somebody solving it last year. I don't have yet to it
and 99 meters per second. Take that. Oh, let's do this.
honestly, I'm just
Meters, double, Double, wait, 4?
Wait, no, it wouldn't be double.
The same stuff twice.
Number 8.
Whoa, wait.
Okay,
Yep, my answer.
so here's the setting where this particular problem takes
Is
place.
this a homemade video? Like, did you video this yourself?
Yeah.
Whoa.
So,
Are you being serious?
That camera's back in 1991.
you guys weren't even live.
Dude, I wasn't
That's
even
when my parents got married.
Yeah,
I wasn't even being thought about.
yeah.
Okay, I always.
Okay,
Show yourself
I wasn't even an embryo.
No, that's my. Does that say
You
May?
will, the one to
Okay,
show
I was
us.
gonna say, it was March 2nd was their anniversary.
So, this is what's known as Victoria Falls, and this is where the Zambezi River falls over a long cliff. It's kind of like Niagara Falls, but it's like Niagara Falls on steroids, because this thing's like 1.5 miles wide. And it's cool because it actually creates so much mist that it creates its own natural rainforest right in that area. This is also one of, I think, only 2 waterfalls in the world that at high water, it produces so much mist that you can actually get a rainbow on a full moon. So, you know, if you've ever seen a rainbow caused by rain with the sun, this is so, the sky is so clear and there's so much, you know, mist coming from that, you can actually get a rainbow at night on a full moon. It's pretty cool to see. And so this little island out here is what's known as Devil's Cataract. So basically what happens is you take 1.5 miles wide worth of river, and then it narrows down into one central point that's about 100 yards wide, okay? It's the Zambezi River Gorge. So if you ever go there, and if it's low water, you can whitewater raft. I highly recommend it. It's one of the coolest things I've done. It's just world-class rapids, and there's the added chance that you might get attacked by a crocodile or a hippo if you get into the water. So that's kind of an added thing. Not to mention the potential parasites you can get if you swallow the water. Here, no, that's not here nor there. So this is kind of the view of what's going to happen. So in 1998, I took a group of 5 kids back with me to Africa, one of which is Mr. Hawkins' uncle, which you will see here in this video. And, well, this is 1991. You'll see 2 different versions, okay? This is, so there's 2 different shots. This is so you can kind of see what it looks like from the side. So, then, so this kind of gives you an idea of the volume. So this is looking up from the helicopter view.
You mean down?
Or yeah, looking down. And so the river up here is really, really shallow because it's so wide. But then it narrows down into, hold on, into this. You just saw like that little side gorge right over there. So this is the kids getting ready to bungee jump. That was Tim, who's now a college professor.
Wait,
this is Katie. She is now a nurse here in Wichita. And so you just, so what happens here?
Where does she work?
Huh?
Where does she work?
I want to say St. Okay?
I heard that mess up your back when you're old.
Hey, if you do it repeatedly.
Did you do it?
I did. They said, you want to do it? I said,
2 inches.
I know too much physics to do this.
How do you get back up?
They just pushed it back up. So what happens is that they make you stare off at the horizon because they found like if you stare down, you tend to like lock up and you won't go. So you'll see him make Tim stare out at the horizon before he basically gets pushed off the edge of the...
Oh my god.
Dude, I
think we need a class.
Oh, never mind.
I think we should try this.
Dude, there's no way. Look at him. He's staring down.
Yeah.
He's like, no.
He's say like 3, 2, 1.
He's clenched up.
Or is he just like...
He's gonna.
Oh, he went.
Okay, so at this point...
Oh god. Oh god.
Well, that's just it. So this is what's set up in the problem. You're going to be in free fall for a while. Okay? So it isn't like the cord immediately starts to slow you down. You're in free fall for a certain distance. Okay? And that's what you're doing in that first calculation. You're calculating how fast you're going at the end of that free fall stage. Then
back up there?
the cord
I
will
don't know, that's what I'm
begin,
saying.
you'll hit the point of the cord. Now, here's the deal. As that cord stretches, what happens to the force acting on you?
Increases?
No. Don't worry about net force. I just want the force from the cord itself. It increases. Gravity is pulling Tim down. So if we're going to stop Tim before he gets baptized into the Zambezi River, we got to slow him down.
Do you actually touch the water?
No.
Okay, good.
No. They do have some.
Like if you could just reach your hand out and just barely touch it.
Yeah, they do have some where you can do that. But unfortunately, one time they miscalculated it, and the guy went BAM!
Oh
And
my gosh.
Yeah, it wasn't good.
But did he
So, not this one. They don't do it this way. So, once this cord starts to go tight, as it stretches, you're going to get more and more and more force exerted upward. Now, you're not going to change the gravitational pull acting down. That's a fixed value. But so as you stretch it, it gets further and further and further. So,
No way.
at some point then,
Oh no. How far do you how do you bounce back up?
they just pull that whole cord back up.
Are
on
you
its way.
serious?
Yeah.
I'd be scared.
Okay, we'll talk about that.
Can we watch
Now
it?
we're at-
No.
now
Now
we're
we
at
watch
The
it.
real part of
That's
it.
an American flag.
I know, that's what I'm saying.
USA.
Okay.
Where was this at? That was in another country?
Yeah, that was at Botswana in Southern Africa. They bungee jumped in those countries.
Why did we get to go?
So,
His favorite class.
here's the setup, right? You're following. Now, you have two distances involved.
Is it negative here? Or just Oh, you didn't even get the same answer than me.
You fall 12 meters, okay, before the bungee cord actually begins to slow you down. Then the bungee cord itself stretches, what is it, 19?
Yeah.
19 meters. So here's the deal. When you're at the bottom here, you have stored a tremendous amount of energy in the bungee cord, right? Which is going to be
You didn't plug the
which is
17
going to
in
be
there.
1/2
19, you mean?
k
In 19,
squared.
yeah.
Now, here's what you have to be careful of. Is this x going to be the 19 meters, the 12 meters, or the 31 meters, which is going to be the total displacement?
19.
19. So this is here. Okay, I got that. Now, what that has to equal is the potential energy due to gravity between this point and this point. Now, here's the reason why I've got to take all of this into account. Because if you were to start here, like when they hoist him back up, they've got to lift him all the way from 31 meters back up here. So your UG calculation has to involve this entire distance of that 31 meters. So that has to be MGH. So if you look at this, you know how far the cord stretches, that's that 19 meters. You know a half, hopefully. You know the mass, you know G, the only thing, and you know the H. So that H has to be the 31 meters because that's the total thing involved in this system. Okay? Got that? So if all goes well, you should get it, because if this is wrong, everything else is going to be wrong. So your answer to 8B should be around 100 newtons per meter.
Ish?
Ish. But not like 3,000-ish.
But like,
Okay? Pretty close, a little bit above 100.
104?
I got
104?
0.04.
You get 104?
How do you say for 8A?
Now, what did,
Okay?
average for 8A? Average for 8A?
For what?
8A?
Your 8A answer should be around mid-teens.
Okay.
8A should be mid-teens.
Yes.
Got it.
Like freshmen?
What the heck?
Hold on.
Like freshmen?
So you plug in the 12 instead of the 19?
That's for different parts. You do the
Yeah,
12 on
because
that one because it's a
look,
free
on
one.
8A you're going to use 12 meters because they're in free fall for 12 meters. Okay? On B, you're going to use the 19 because that's how far it gets stretched. But then in your UG calculation, you've got to use the total length of 31 meters. Okay? Got that. So your value of K should be a little bit above 100. So you know everything here except for K. Okay? Okay. Okay.
And then
Are we good with that?
are we gonna do D?
Okay. Now, when you get to D, here's the deal. When you're here at the bottom, okay, what are the forces acting on you? At the very bottom, what are the two forces acting on you?
The spring and gravity.
Gravity's pulling down, and the force from the
Spring.
bungee cord to the spring is acting up, right? If you're going to stop, which one has to be bigger?
The spring.
Yeah, the bungee cord has to be bigger. Otherwise, you're going to keep falling, and that's bad. Okay? That's very bad. So, at the very bottom, the bungee cord has to be bigger than the force of gravity. So, I have two different forces acting in opposite directions. From that, I can determine the net force. Oh! So my net force is going to equal the force from the bungee cord minus the force due to gravity. What does my net force equal?
KX.
No! Don't make this difficult. MA! Okay? Net force is MA. Boom! So, how can I calculate, what two things do I need to calculate the force from the bungee cord?
K and X.
K and X. Do I know my K?
Yes.
Yeah. Do I know my X?
Yes.
Yeah, because that's how far it stretched, 19 meters. And then this is just going to be, what's the only thing that you don't know? Is that acceleration. That's why you had to find your K value first.
MV. Is that it? Oh, that's not it.
So we don't need it.
Is this recording right now?
Yes.
I was just making sure, because
Except you don't even
it seems
need
like there's a
those
lot of
M's.
confusion.
I know. That's what we're kind of
There's
doing.
probably going to be a lot of confusion.
So, when you get done with this acceleration, that value of your acceleration should be something close to the legal drinking age.
Did you get it right? I don't know, I'm still working.
Oh, I guess it's
So
at
the
the
X is double, so.
What's K measured in?
What?
Meters?
On
Per
8E,
meter. Newtons per meter.
that acceleration should be something around the legal drinking age.
Somewhere around 12.
Wait, who?
United States?
Oh, no. X is how far the cord stretches. That's 19 meters. H is the distance from the top of the bridge all the way down to the bottom, which is 31.
8E, drinking age.
Yeah. When this, define the value of K.
Okay, cool.
This is the 19 meters because this is how far it stretches. That H is the 31 meters because that's the total amount of transfer of energy that you're going to store due to gravity. Okay?
On E?
So you know everything but
Oh, I guess I
K.
should write a little bit out. Don't trust you anymore, Matt.
Then when you get K, that's the K that comes down here.
Oh, crap.
Eric?
Yes.
Huh?
There's two.
So we'll use 19 correct on that one?
For this one?
Yeah.
Yeah, because that's your maximum elongation. That's when you're going to get maximum upward force.
So am I supposed to square that 19? This is a simple algebra problem. Do I square that 19 or do I divide by 19 and square it?
No,
That's simple. I square it.
Okay.
Better yet, you solve for K first and then put in the numbers. If you really want to run with the big dogs, solve for K and then put in the numbers. So basically multiply by 2, divide by X squared.
Oh, that's all you have to do?
That's the big dog way to do it.
Was that the one you were stressing out about last night?
Yeah, I was
19 on the left side, 31 on the right side, on the left side. You gotta use the kinetic energy way, and then on the right side, you gotta use the whole way.
I mean, I don't think it's a big deal.
Yeah.
31.
What is
Are we
the maximum
good?
acceleration?
Okay.
Our equation for acceleration.
On number 6, every answer on number 6 should involve a 6. Oh!
Thanks for the help.
What if they're real close to a 6?
Okay. Now, on number 6 and 7, I beg of you, draw the chart so you know what type of energy that you have. So let's make sure everybody's cool on number 6. What's your energy constant on problem number 6?
Kyle.
So why does it not 2?
What's the energy constant on problem 2 joules? Okay? 2 joules is your energy constant on number 6. So that means at any point, all of the energies have to add up to 2.
So where did you get the 1.6? Oh, from right here. So to this number. Gotcha. See, I calculated it out. I just didn't put down the right thing.
Yes, that's your energy constant.
I gotta throw. I gotta throw. Doesn't matter. I get there. So how many times have you thought about it?
Now, let me talk about this graph on 4A.
Off by like.
Okay? So this is what your graph is going to look like. Boom, Hooke's law is linear function. Okay? You know, this point, you know, the other point is 0. Basically, you're finding the slope of the line using f equals kx. Now, here's what you cannot do on a spring problem. Listen to me. This is what you cannot do. So if I tell you that this thing, I think it's like, I don't know, let's just say that it's 2 newtons. And let's say this is 0.1 meters, okay? Whatever it is. If I ask you to calculate the work that's done, here's what you cannot do on a spring. Listen to me. This is what you cannot do. You cannot go, oh, work equals force times distance, and you take 2 newtons and you multiply that by 0.1, and you get 0.2 joules. You cannot use this on a spring graph, and here's the reason why. I'm not applying 2 newtons of force over this distance. What I'm finding is this area. Okay? So on a spring, you cannot do this. Okay?
I didn't do that.
No,
you
yeah,
can
we did.
use a triangle and use 1/2 base times height. That you can do.
Yeah, I just
Or
put it
you
in the
can
negative.
find like the average force, which is what happens if you take 1/2 times F.
For what?
Okay?
Yeah.
But
It's
you
196.
cannot do a straight force times distance idea.
Times 0.1. So, oh shoot.
So your answer to 4A should be around 20.
What about B?
B? Ooh, a really small number.
Like to the negative 2 or to the negative 1?
To the negative second.
Am I right?
You're right. Okay. What did I think I divided it. What are you supposed to divide it or multiply it by? Is it?
Huh?
Did you find us?
Oh my God, brain.
Because you can't do, he just said you can't do that.
That's exactly what I did, didn't I?
So is B a very
You know the spring constant on 4C. You have the value of F. You have the value of K. So basically, it's the linear function.
So now whenever you find
You're just going to use this.
S equals
You know the value of K.
X.
Because that's what you found on A.
I'm feeling pretty good.
Is 4B under 0.1?
Yes. Yeah, 4B
What's your
is
X?
close to 0.1.
Oh, 0.1.
No.
Oh, Skippy, wait until after Thanksgiving.
No, Maddie, I don't trust you anymore. You steered me down the wrong path.
If you're closed-minded, but it doesn't. You have a perspective of the world.
So,
Is number 5 the same?
you've got a point here, which is the force and your distance. And you have the other points you
Both objects.
Because that's the
This is just a linear function of f equals k.
Whatever on that one.
Okay, so Maddie's the lab that you're going to do today is reminiscent of the very first lab that you did when you walked in this room many moons ago. So here's the setup. Now, there's one variation that I want that you need to change. On the very front of the lab, it shows this setup with like a hook clamp on the front and then just 3 rings below that. My hook clamps stick out too far so that you can't oscillate in the middle. So don't set this up with a hook clamp. Go ahead and put a ring on top with like a piece of metal or a pencil in there so that way you can adjust where the center of that spring is going to oscillate.
Is this a lab? Like, are we
Just said.
What? Oscillate twice. I call it
That's
oscillate.
another one.
Can I just give you our vocab?
Yeah. You know, you can just keep saying vocab words. That's
I like
great.
it. We get
What
extra
did I
credit.
say?
Oscillate.
Oh.
Can I just give you my list and then you? Because every
Yeah.
time you say one, I get extra credit.
Okay.
Okay. Cool.
And every time an English teacher says a physics equation,
Do I get extra credit? Really?
like that's going to happen? No. Okay. So here's what we've got. The first thing that you need to do is make a decision about where you're going to set this first ring. So this ring needs to be where you can measure from where the spring is in equilibrium. So you can either set this ring where the top of the ring is level with the bottom of the spring, or you can set the bottom of the ring where it's level with the bottom of the spring. I don't care which one, but you have to make that decision so that you know where to measure from. So I'm just going to go off the bottom, though it doesn't make any difference as long as you're consistent. So the first thing that you need to do is get data to fill out the data table on page 2, where we're going to determine the spring constant of this. So what you're going to do is you're going to hang different masses from here, just like you did the very first day that you were in this lab. So here's a 0.5 kilogram mass. 0.5 kilogram mass exerts a gravitational pull of 4.9 newtons. So I'm going to hook this up. I got 4.9 newtons. So then you take your measuring device that allows you to measure to a pretty decent precision, and you're going to measure either from the top or the bottom of this ring down to the top of the hook. Okay? So that's going to be a data point. So what you're going to do is you're going to put more and more and more mass on here to stretch this thing further and further and further. You're going to use that to generate a point. So you're going to have a graph eventually that's going to look like this. Now, the very first day that you were in here, you graphed, what did you put along here? Force or elongation? Force. Why? Yeah, that was our independent variable. The problem is that our units won't work out with energy if we do it this way. So on this graph, we've got to put force here and elongation here. Okay? So you're going to have points. You can draw a best fit line, draw the line, circle the points, boom, find the slope of the line. Show me the work. You can only use data points if the data points are actually on the graph. If they're not, you can't use those data points. Now, eventually, when you get to the point, you are going to come out here, and I'm going to tell you to use a maximum elongation. Okay? This will make sense when you get to like page 2. So at some point, you're going to find the area underneath this curve. When you do that, find your maximum elongation from your data. Come up here, and what you're going to use as the height is the point that actually matches that force. You can't use the data point that goes with that elongation unless it happens to fit on this graph. So when you get to that point, and I lay that out all in the instructions, You're going to come out here, you find your maximum elongation. Come up here, find this point, that's what you use as the height of the triangle. Not necessarily the force that corresponds with it, depending upon how close your data is to this line. Okay? So when you get to that point, that's what you're going to do. So you're just going to hang more and more and more weight on there, get the data. Now, to do the second part of the lab, you don't actually have to have this slope. So you can collect all of the data before you crunch any numbers. So that's just the first thing that you need to do. Hang the weights, get very precise data, generate the graph, boom, here we go. Now, here's where energy comes into it. So over there on page 2, what we're going to do is we're going to look at how energy changes. So what we're going to do is we're going to make this thing oscillate, and I'm going to put a 1 kilogram mass on here. Okay? So if I pull this down, okay, we get this action going. So what type of energy, there's 3 types of energy involved in this oscillation. Kendra, since I gave you some points in English for using the word oscillation, what's one type of energy that's involved in this deal?
Force gravity. No. Oh, energy.
Yes.
Energy.
Energy.
Okay. I'm sorry. The kinetic energy.
Kinetic energy.
Thank you. Okay.
Okay. Why does it have kinetic energy?
Because it's moving.
Because it's moving. Okay. We have some kinetic energy. So if you look at this in terms of like containers, I'm going to have a kinetic energy equation or container because of the fact that it's oscillating. Garfield, what's another type of energy I'm going to have?
Potential.
Of what type of potential?
Us.
Us? Why am I going to have us?
Because it's a legit spring.
Because it's a legit spring as opposed to a non-legit spring.
Yeah.
Otherwise known as just a string.
Yeah.
Or a wire.
Yeah.
Stranger here
It's
today.
actually spring.
Okay?
I just didn't notice.
So I'm going to have some of this, and there's a third one. Meat. What's my meat? Cheese 2.
Cheese head.
It is up. Okay? It is up. Okay?
So you got 3 cups.
So I've got 3 cups. So basically what I'm going to do is I'm going to continuously change. I'm going to continuously change the levels between these 3. Okay? Now, so as this thing oscillates, let's talk about the kinetic energy one first. So as this thing oscillates, does my kinetic energy mug ever go to 0? Container.
Oh. I thought mug was a whole new thing. I was like,
no. Somebody said mug. Okay, container. Does my kinetic energy container ever go empty?
At the bottom?
Yes.
At the bottom and at the top. Why?
Because it's changing direction.
Yeah, because it's changing direction. Therefore, the velocity goes to 0. Therefore, I have no kinetic energy. Okay? So at the top and the bottom, I have no kinetic energy because I have no velocity. Right? Now, does my us container ever go to 0?
No.
No. Why?
Spring's always there. Spring is always there.
Okay?
spring is
There's
always
the
springing.
spring. Do I have any us?
Springing.
But do I have any us up at that point?
Us is equal to.
No. Why?
It's not being stretched.
It's not being stretched. Okay? Since I have no value of x, I have no stretch. So when this thing is oscillating, okay?
That's right there. It's always stretched.
Okay? So do I always have some us?
Yeah.
Yes.
Unless it like went back to the original.
Unless it went all the way back up here.
That would be admissible.
It would be, but we're not going to do that. So I don't have any, I never reach a point where my us goes to 0. But does my us change?
Yeah.
Liz, when is my us biggest? When I've got my maximum elongation. Us is the minimum at the top of the oscillation, right? Okay? So my us container never goes to 0, but it does change. Okay? Does my up container ever go to 0? No. Why?
No, it's got mass gravitational acceleration.
It's always above the ground.
And it's always above the ground, right? So what we're going to look at, though, when we talk about UG, what we're going to look at is the change in potential energy between these 2 points, between the bottom of the oscillation and the top of the oscillation. So my UG at a maximum is going to be when my mass is at the top. It's going to be at a minimum when it's at the bottom. So here's what I want to look at. So when I'm at the bottom of the oscillation, my kinetic energy is, my kinetic energy is at the bottom of the oscillation. What's my kinetic energy? 0. My us is at a maximum. My us is at a
What?
excuse me. My UG is at a minimum. At the top of the oscillation, no kinetic energy. Us is at a and UG is at a maximum. So what I'm doing is continuously exchanging these types of energy. So if I have no kinetic energy at the top and I have no kinetic energy at the bottom, when do you think I have maximum kinetic energy? In the middle. In the middle. Okay? So it starts at rest, speeds up, hits maximum velocity at the middle, and then it starts to slow down again. Okay? So what makes it slow down on the way down? Which force, Kendra?
Us. The spring. What? Oh, force! Gravity.
Kendra.
I'm sorry. Okay.
Kendra.
Okay, gravity.
Okay, Kendra.
Yes.
Okay.
What?
This is the same discussion I just had with Garfield during encore. Okay.
Okay.
You're listening to respond and not listening to learn.
Hey,
Okay?
I.
Shh. See?
Yeah.
Okay. So, Kendra,
Yes.
Yeah, it's okay.
at the bottom,
He said that
which
to me,
force is making it slow down? Gravity or the spring?
Gravity.
That's the
What do you mean?
Okay. As this thing is stretched down to the bottom,
Yes.
what are the 2 forces acting on it?
The spring and gravity.
Yes? So which one is going to make it slow down? Gravity or the spring?
The spring?
Yes, because that's exerting an upward force.
Okay.
Okay?
Okay.
Now, as it goes up, which force is going to make it slow down?
Gravity.
There you go.
Okay.
Okay. Okay. I gave you the force shot.
Well, I was like sitting there like.
All right. So, when you make this thing oscillate, and this is a little bit tough to do, so you don't need these springs until you get to the second part. So, what you're going to do when you get to the second set of data, this is where everything has to be lined up just right. So what you're going to do is you're going to make this mass oscillate like this. Okay, but it's got to oscillate just in the middle. Obviously, if it hits the rings, that's bad. So what you want to do is set these 2 rings. Once you set this ring, this equilibrium ring never changes. So what you want to do is set these rings where this ring is at the top of the oscillation and this ring is at the bottom of the oscillation. So you can go like this, okay, like that's going to be, go down some, and then I got some action like that, okay? So obviously if you have a bigger oscillation, that's going to change. So what you want to do is get it oscillating and then set your rings. And it's tough to do because you're kind of looking at it going, yeah, if you really want to get picky,
So,
slow-mo it, and then you can adjust your...
Where's the top?
Is that going to go forever?
No, why won't it go forever?
Gravity.
Why won't it go forever?
Net force.
No, no.
Friction, transfer.
Friction. You're changing it into thermal energy. So on an atomic level, this spring works because these atoms that make up that spring get stretched. They don't like it. They go, oh, this is bad. I want to go back to hanging out with my mates. So they come back together. So as these things move, you generate a certain amount of thermal energy in the spring. Now,
Wait, hold on.
So
the
cordial horses.
So if it's super, super hot in here.
Stop.
If it's super, super hot, as opposed to just super hot.
Then the heater is probably on high.
Or it's really hot outside and the air conditioner is broken.
You're not broke.
Correct. So like there's not going to be as much friction, right?
Shut up, stop talking like that.
No, there'll actually be more because like resistance increases.
Obviously.
So if it's cold, it's going to keep on going.
Yes. But now, but
Let's
that's,
put this in a freezer.
it's a little bit of difference, but not enough to make any
If
difference.
it's like-
Frictionless
if
room,
it's close to
perhaps.
absolute zero, then you're getting
And in a vacuum, then, yeah.
you're getting
Yeah. So
Someday.
here's the deal.
Let's get that.
You're going to generate a certain amount of thermal energy. Now, it isn't like, oh, I need to make a spot of toast. I'll have a spring oscillate and I'll put my bread inside and it'll warm it up and toast my toast. No.
That would be so
Okay?
cool though.
Heck yeah, bro.
It won't work. Okay? Or even if you grab it, I'm not going to make you wear heat gloves when you touch the spring like, oh, ow. No. Okay?
Ooh. It's obviously not gonna play.
Thank you.
Approximately 89.
Thanks, Hunter.
Okay. Stop. That was just wrong. Okay? All right. So you're also got some interaction with the air. Okay? So you got some drag going on. So the great dissipator of energy is always friction or thermal energy. That's always where it goes. So the amount of energy in the room is still a constant. We're just changing its form. So on the diagram, you have to get these values right or all of your calculations are jacked up. So on the front, you have three different distances. So here's your top ring.
Can me and
That's where the
Hunter
spring
actually
is.
get lap thing?
Huh?
Can me and Hunter get on lap
I thought I gave them to you.
No, you didn't. So we didn't want to interrupt you.
Yeah, because you've
Remember
been
that
talking
playing
about some
We did that one time and he yelled at us, so we just said, yeah.
Don't ask me while I'm lecturing.
Mr. Burkham, I wouldn't lie to you. We do not have sheets.
Why? I'll have to print them out.
When's the next feminist
Get one for somebody.
Yes.
Okay.
Well, then they won't have one.
I don't care.
What?
When's the next
All right.
First
Kendra?
What?
Thursday of every month.
No.
Well, how about we have
No.
Thanksgiving club meeting?
Yeah.
Yeah, I'm gonna
There
be
you
out of town, so.
I mean,
Lexi,
I'll
being
hold
a kind
it.
and generous person
So we don't
and caring about others.
Alright, so I have a real quick question.
Our student
So you set up those
I voted
rings
for
like.
you.
Oh, did you vote for
Yeah,
me?
so this, let me, I'll show
No,
you.
you
Alright.
didn't.
Yes, I
Okay.
Really?
because I knew you were.
I
So,
bet Justin Jones would have given you his paper.
You didn't write it, Jake.
so here's what you've got. This is your equilibrium ring. That's where the ring is at when there's no stretch to it at all. So this is the ring at the top of the oscillation. This is the ring at the bottom of the oscillation. So this thing is going back and forth between these points. So let me explain the math behind this. Forget that anything else exists. Forget that literally nothing else is here. If I said, how much potential energy do I store in stretching that spring from its equilibrium point down to this point? How could you find the us that's stored there? What would you need? You need the value of K and X. So that us right there is going to be 1/2 K times X1 squared. Okay? So to get this spring to that point, to get it from here, to stretch it down to this point right here, that's a certain amount of energy that I'm storing. Right? Now, to get it down here, that's going to be more energy that I'm going to store because I'm going to stretch it a further distance. So with that one, to get it from this equilibrium point all the way down to here, that's going to be 1/2 K times X2 squared. Don't worry about H for now. We'll talk about H later. So this is the energy that I have at the first ring. This is the energy that I have at the second ring. Which energy is going to be bigger? At X2 or at X1?
X2.
X2 because I've stretched it
Furthest.
farther. So the difference in this energy during this oscillation is going to be the us at 2 minus the us at 1. Right? So my us at 2 is 1/2 k x2 squared minus 1/2 k times x1 squared. So what can I do here to make this a little bit simpler?
Take out K.
Factor out a k and?
And a one.
No, these x's are different.
A 1.
A 1/2, right? So I can write this as 1/2 k times x2 squared minus x.
Should we write that down?
It's on your sheet.
Oh, it is?
So over on page 2, this is how you're going to calculate the energy stored in the spring. Okay? This is what you're going to do. Now, what we're going to do is we're going to compare that to the gravitational potential energy as it goes from this point to this point. So the gravitational energy change is going to be based upon this value of h, which is just going to be literally mgh. So you're going to know the mass, you're going to know g, you're going to know h. So this is vital that you understand where these measurements are. The x's are measured from the equilibrium point because that's a reflection of how far the spring has stretched. H is a reflection of the height, okay, because of the fact that that's how far that potential energy is changing in between these points of this oscillation. Now, at this point, if I completely stop it, what are x1 and x2? Or they would basically be the same thing, right? Yeah. So if x1 and x2 are the same thing, guess what? I'm not having any change in my us, right? Because it's not oscillating. Guess what? My value of h goes to 0. It doesn't oscillate because I'm not having any exchange of energy. But once I begin to make it oscillate, okay, now I have an exchange of energy. Now I'm trading us for UG for kinetic. And it's just a symbiotic trade between those three containers.
Is H measured from the ground?
No. H is just this energy change right in here.
From the lowest point?
Yeah. So this is H. This is X1. This is X2. That's H. Okay? So you have to have those measurements right. Now here's what I don't want you to do. Don't pull this thing down and set your ring and then let go of it. It won't go to that point. What you want to do is get it oscillating and then set your rings. Okay? So what you want to do is you want to do 3 trials. At a minimum, use a 1 kilogram mass. So what you want to do is have like a smaller oscillation, call that trial 1. Then you want to have a bigger oscillation, call that trial 2. And then set up a 3rd trial where...
Holy cow.
Yeah. Now, if you do this, and it hits the floor or hits the table,
Just leave it off the edge.
yeah, just leave it off the edge. So if that happens, just do this. And by the way, make sure somebody is holding this down or it falls off, in case you haven't noticed. So then, you can have...
Whoa, look at the...
Okay.
A long
Yeah.
obsculation.
That's just so wrong.
He's not wrong.
Well,
Oscillation.
so it's actually easier with the bigger mass because it oscillates slower. Okay, so it's almost easier to see it with that. But make sure somebody's holding this back. So here's what you want. You've got a half an hour. Get the spring constant. Get all of your data.
20 minutes. 20 minutes.
Okay, you have 20 minutes. Hang the weights. Just get the data. Make it oscillate, get those, then crunch the numbers later. You don't have to have the value of K to get your oscillation data. Okay, you're on your own, go.